Okay.
I will give all the time. You can have some questions or
if there's anything which you want to ask for clarification, do that during the talk. Otherwise, we'll keep the discussion until the end. Okay? Right, thanks. Okay, so this is a continuation very much of the talk a couple of weeks ago. I thought about what I would do for this second lecture, and originally I thought I would go into some more detail on carbon footprinting, but actually I think it'll probably be more interesting for you if I go through a couple of examples. So that's what I'm going to do, but before we get there, just a reminder of what we're talking about. We're talking about using life cycle assessment, which is a form of system analysis. So if we're looking at an energy system, and I'll interpret that quite broadly to mean a system which generates or uses energy. And we're looking at the interactions between the economic system, the energy system, and the surrounding environment. So we'll look at this in terms of the inputs of raw materials and energy required to deliver some service, and also the emissions, and of course I will continue to concentrate on the emissions which contribute to climate change. So this is topical, I think, in the run-up to the meeting which is to happen in Paris in a few weeks' time. And to remind you also of what is the nature of life cycle assessment. Life cycle assessment is a kind of analysis in which you look at a complete supply chain. So it might be a complete supply chain providing a product, or it can be a complete supply chain converting primary energy into some usable end form, and that will be one of the examples I will take today. And rather than going through the details of life cycle assessment, let me just give you a bit more of the background principles which you will need to follow the examples. When you're doing a life cycle assessment, and let me make it quite clear, a life cycle assessment is extraordinarily time-consuming. So you don't embark on it unless you're serious. It really takes a lot of time and effort. One of the problems which arises is this. The first step, strictly the second step, but the first real step in carrying out a life cycle assessment is to compile what is called the inventory. So this is the identification of the inputs and the emissions from the system which delivers the final service. When you're compiling that set of data, which is called the inventory table, you frequently run across a problem which is called allocation. Now this is one of those features of life cycle assessment which causes great argument between the people who like me, who actually do life cycle assessment seriously. I'm not going to go into that argument, a lot of it is unproductive, but what I will do is introduce to you the problem which allocation addresses. It will frequently happen when you're analysing that supply chain that one or more of the processes in the supply chain delivers more than one function. And when that arises, you have to ask the question, how should those exchanges with the environment, the environmental interventions, how should they be allocated between the different functions of something which provides more than one function? And some simple examples are energy recovery from waste. I touched on that last time, the way in which you do the accounting for energy which is recovered from waste. It's also a big problem, of course, if you're looking at a combined heat and power plant. because the two functional outputs there are obviously the heat and the power. But it also arises all over the place. For example, if you're doing life cycle assessment applied to agriculture, a farm will produce, say, wheat, a cereal, and that cereal contains both grain and straw. And how do you allocate the environmental interventions associated with the farming activity? How do you divide them between the grain and the straw? So there's a whole lot of general problems here. They are addressed in the international standards on life cycle assessment, and I'm not going to go into those standards in detail, but what I will do is introduce you to the preferred way of doing allocation, which is by system expansion. If you look in the international standards, it will tell you that you should do system expansion as your way of doing allocation wherever you can. There are alternative approaches if for some reason the system does not lend itself to doing system expansion. So let's see what system expansion entails. Let's suppose that I've got a process which delivers two products, for example, power and heat from a combined heat and power plant. And there are inputs and emissions associated with operating that process. So the allocation problem is, how do I allocate them between the two different products? Well, system expansion says, focus on the product which you're particularly interested in, for example, product 1, just call it number 1, and try to find an alternative process which can provide product 2 without product 1. So there you are, there's the parallel process B. So process B will have its own set of environmental interventions, which it uses to deliver product 2. So if I now put these two together, I have a combined process, A and B together, which deliver those same two products. So I've expanded my system. I've gone from process A to process A plus process B. And why does that help me? Well, it helps me because I can now vary the output of product 1 without changing the output of product 2. Because what's happening is if I increase the activity of process A, it produces both 1 and 2, but product 2 displaces the output of that product from process B. So this system expansion approach gives me a way of saying, how do the environmental interventions vary with product 1 and keeping the output of product 2 fixed? So if you think back to what I said about energy recovery from waste, there's an example of it. If we're recovering energy from waste, then that energy replaces the energy conversion which goes on in the background economy. Okay. So system expansion is a very important approach, and the reason I've mentioned it here is that when you're looking at using life cycle assessment to make fairly high-level policy recommendations, you need to refer to system expansion as a way of making sure that your comparisons are valid. And you'll see some examples of that. You always got to ask, okay, if I'm introducing a new process, what effect does it have on the existing economy? It's not, you can't just make that one product in isolation. You've got to ask, what else could I use the inputs for example? Now, further thought before I move on. Life cycle assessment is a form of system analysis, system thinking. And there are two really different approaches to system thinking. Life cycle assessment is an example of what is usually called hard system analysis. That's hard as distinct from soft, not hard as distinct from easy. Okay? Hard system analysis is quantitative, and your approach to the system is to look at operations, components, which are linked by flows. These will most obviously be flows of materials or of energy, or there could also be flows of money in some applications of system analysis. That's a bit outside life cycle thinking. So hard system analysis, you identify the system by the flows of materials, energy, or money. Soft system analysis is not usually quantitative, but it's nevertheless very important. And the key work on soft system analysis was carried out by Roland, who wrote 2 very good books on the subject. So if you're interested in getting into soft system analysis, and I'm going to give you some examples of soft system thinking. If you're interested in soft system analysis, I recommend that you start with Roland's books on the subject. They're called something like Systems Theory and Systems Practice. The difference is this. In hard system analysis, the linkages between the different parts of the system are represented by flows. In soft system analysis, the linkages are represented by influences. So it's much more qualitative, in fact it's necessarily qualitative, usually. So in soft systems analysis, you might say, if I change this process over here, it's going to change the way other people behave in whatever processes they're involved in. So the linkages are usually in terms of behaviour or management practices or overall governance, rather than directly flows of materials or energy. So the soft systems approach is particularly important when you're looking at government systems, legislation, regulation, or management. Okay? But usually, if you're applying system thinking generally, you need to have both approaches in your tool bag. And you'll see that from some of the examples. Okay, so I've now sort of cleared the ground, and what I'm now going to do is go through a couple of examples. I'm going to start with hydrogen, because there's always some interest in hydrogen as, well, hydrogen is not a fuel, it's an energy carrier, and that's a key point which we'll be exploring. And I'll also apply the same thinking, life cycle thinking, system thinking, to say something about buildings. So I'll particularly start with zero energy buildings, because that's a current interest. And we'll then say a bit about buildings in the context of a city, an urban area, part of an urban metabolism. And I'll also say something about behavioural aspects, which is where the soft systems approach will really come in as basic and important. Okay, so let's start with hydrogen. One of the reasons I thought I'd put hydrogen in here is that, to be blunt, there is a lot of nonsense talked about hydrogen. And there have been books written on the hydrogen economy which are frankly so ill-informed that they're not helpful. I won't name names, but this is part of my general recommendation to graduate students. Really sharpen up your critical faculties. Just because something has been written and published in a paper or a book, it doesn't mean it's right. That applies to my writing as well, by the way. The only thing I've ever said, which is absolutely and fundamentally true, is just because it's published, it doesn't make it right. Okay, that statement is scripture. Right? So let's start with hydrogen as an energy carrier. Why do I emphasise energy carrier? Well, people sometimes refer to hydrogen as a fuel. And it isn't, because hydrogen doesn't exist in that form. You have to make the hydrogen from something, and making the hydrogen requires energy. Okay? So you input the energy to producing the hydrogen, which you might use somewhere else. So hydrogen is a vector, or a storage medium. It's a way of taking energy from one form and using it somewhere else. Okay. So it's different from things like gasoline. I mean, gasoline starts life as oil in the ground. It's much more like electricity, because it has to be generated, and that generation requires an energy source. So the issues in using hydrogen as an energy carrier have to start with production. How do you make the stuff in the first place? Having produced it, very rarely do you make it at the point where it's used. Now, there are some cases, and I'll show you one of them, where you can actually make hydrogen at the point of use, but they're fairly rare. You then have to think, how are you going to use it in the end? And you also then got to ask, if I didn't use the energy to make hydrogen, what else could I do with it? And would converting the energy into hydrogen actually represent an improvement over the alternative uses of the energy? That's where the system expansion thinking needs to come in. Okay, so let's start with how can you make hydrogen, the production step. Basically, there are two ways of doing it. You can do it by electrolysis, which means splitting water into hydrogen and oxygen. And of course, that approach to making hydrogen appears to be quite simple on the surface, but of course, when you get into the details of it, how you set up an electrolytic cell to carry out that electrolysis, that's not straightforward. And the efficiency of doing it is less than perfect. Furthermore, of course, this is the real point, you have to have surplus electricity available to you in order to be able to make hydrogen by that route. And the example I'm going to show with a few photos is Iceland. And to tell you why, Iceland has almost 100% renewable energy, comes mainly from geothermal sources, and Iceland is one of the places in the world which has a lot of surplus electrical power. So if hydrogen by the electrolytic route is going to be attractive anywhere, it's likely to be Iceland. I'll come back on that. Oh, and by the way, don't go thinking that geothermal energy is climate neutral. When you extract geothermal energy from the sort of volcanic sources that you have in Iceland, there are significant emissions of greenhouse gases associated with that extraction. You can actually smell them when you drive in from the airport at Keflavik regularly. So, if you're not going to produce hydrogen by electrolysis, for example, because you don't have surplus electricity, how else you can do it? Well, you can do it from carbon-based fuels, hydrocarbons, for example. To do that, you usually need a large chemical plant. I'll look at the reactions shortly. And one of the most convenient feedstocks for producing hydrogen from a carbon-based fuel uses methane, or natural gas. You can convert methane to carbon dioxide and hydrogen. You can do it in a large chemical plant, or you can do it on a small scale, and there are some demonstration schemes which have been tested in various parts of the world, where you deliver methane to, for example, a household. You convert the methane by reforming it to hydrogen, and then you use the hydrogen in a fuel cell. Okay? It turns out that that's actually not very efficient, and I'll show you why. Sometimes hydrogen is available as a byproduct from other processes using hydrocarbons, usually oil refining. And hydrogen has been available from refineries in some parts of the world, refineries usually which treat what are called light crudes. These are forms of crude oil which have a relatively high ratio of hydrogen to car. Sometimes those fuels will generate surplus hydrogen. That is ceasing to be the case, though. Hydrogen is becoming much more scarce. And here's an example of soft system thinking. The reason why hydrogen, one of the reasons why hydrogen is becoming less generally available from oil refineries is changes in the regulations over marine liquid fuels, which may sound a bit perverse, but I'll try to explain quickly why. Up until really quite recently, marine diesel fuel has had a very high sulfur content, 2% is typical. The reason for the high sulfur content of marine fuel is that the refineries use marine diesel as the place where the sulfur goes. That's the sulfur that comes in with the crude oil. Okay? So the crude oils contain some sulfur. The sulfur has to go somewhere, and traditionally the sulfur has ended up in the heavy fractions, of which the largest is the marine diesel fuel. The pollution caused by high sulfur in marine fuels has in some parts of the world become an embarrassment. There was a study in the European Union about 5 years ago which found that the single largest source of acid gas emissions in Europe was marine diesel. So by international agreement, the International Maritime Organization has agreed standards to reduce the sulfur content of marine diesel in order to reduce the problem of acid gas pollution and also acidification of the oceans when the ships go over it. Okay, so that all sounds perfectly reasonable, but if the sulfur's coming out of the marine diesel, it's got to go somewhere. So the refineries have had to change what's called the refining pattern to do more of what's called hydrodesulfurization. You basically produce hydrogen sulfide and react it to get elemental sulfur usually. And that requires hydrogen. So there's an example of soft system thinking. Reducing the sulfur content of marine diesel fuel has had the effect of making hydrogen more scarce, because more of it is used in the processing to get rid of the sulfur. Okay? So that availability of hydrogen as a byproduct from oil refining, that's possibly a thing of the past, and it's certainly already only the case in certain locations, of which California is one. It's become much more scarce in Europe. I'm not sure if you can even get hydrogen from oil refineries in Europe anymore. Okay? So the two main sources of hydrogen are electrolysis or chemical reaction, usually starting from methane. Having made it, what do you do with it? Well, unless you can make it at the point where the demand arises, you have to transport it. And how can you do that? You can do it by pipeline. Now, in the early days, when people were enthusiastic about the so-called hydrogen economy, they said, oh, well, that's easy. We'll just transport the hydrogen in the gas grid which you already use for transporting methane. Actually, that's not a very good idea, because you have to change the materials of the pipelines, because hydrogen causes the metal to go brittle. That's been known since the 1930s, but it's one of those things that kind of got forgotten along the line. So distributing hydrogen by pipeline is a possibility. You can alternatively condense it to a liquid, quite low temperatures, so it's a cryogenic liquid, and you can transport the liquid. You can transport it as a compressed gas. That means transporting it at a much lower density than the cryogenic liquid, so the volume of the containers that you have to ship around is quite large. And you can perhaps avoid any of that by storing the hydrogen as metal hydrides or compounds like sodium borohydride. There's been quite a lot of work done on storing hydrogen in those condensed forms. Okay, well now let's look at those. One of the uses which has been proposed for hydrogen in the past is for powering aircraft. In principle, you could use it as a jet fuel. When you look into it, you find it doesn't, well, sorry for the pun, it doesn't fly. The reason it doesn't fly is that the energy density is wrong. There was a serious attempt to design an aircraft which ran on hydrogen stored as a cryogenic liquid in the wings. But even as a cryogenic liquid, the energy density, that's the energy content per unit volume, is much lower than for conventional jet fuels. And if you look at the designs for hydrogen-powered aircraft, they look ridiculous. It's like a whale with wings on. And all the extra volume is what's needed to transport the hydrogen. Compressed gas is even worse for aviation, and the metal hydrides, sodium borohydride, are simply too heavy. Actually, it's the opposite extreme. It's worth bearing that one in mind because the aircraft aviation sector is one of the ones which is going to be most affected by whatever comes out from the negotiations in Paris in a few weeks' time. Because the aviation sector is really stuck for an alternative to hydrocarbon fuels. Hydrogen is not a viable alternative for aircraft. Okay, so there are the distribution and storage problems. Now let's go back to producing hydrogen. If you're going to produce it by electrolysis, you have to have spare electricity. If you've got spare electricity, there are other things you can do with it. In Iceland, it might make sense because they have surplus electricity. In other parts of the world, if you've got surplus low-carbon electricity, you tend to store it so that you can use it at times when demand goes up. And that's the intelligent approach which has been taken in Portugal. I can't see hydrogen being viable ever in Portugal, to be honest, but that's by the by. So you have to have a consistent surplus electricity in the supply for the electrolysis route to be viable. Iceland is about the only place where that applies. Maybe New Zealand, for similar reasons, a lot of geothermal. If you can't make hydrogen by electrolysis because you've got more beneficial things to do with the electricity, then you can make it by chemical reaction. So you can turn natural gas into a liquid fuel. So if you start with methane, I'm sorry, I just realised I didn't include the chemical reaction anywhere, did I? Oh, yes, I did. I lost it. There it is. Right. No, I lost it. Sorry. What you actually do is react methane, CH4, with oxygen from the air, and you produce carbon dioxide, CO2, and hydrogen. Okay? Eventually, you're going to end up with carbon dioxide and water. Okay? You can either burn the methane directly to produce carbon dioxide and water, or you can convert it to carbon dioxide and hydrogen and burn the hydrogen to make water. Thermodynamics tells you that whichever route you go, you end up with the same energy yield. So you're starting with the same inputs and converting into the same reaction products. So I can now compare the carbon emissions associated with different ways of using hydrocarbons. Okay? And my base case, okay, the reference case for system expansion, is going to be conventional gasoline cars. Now, you can find all sorts of analyses reported in the literature, but the figures I've shown you here are results from an analysis, a comparison of all the different analyses, and I got them from a friend who was at the time the research director of Air Products, big company with an interest in gases, because Air Products were wondering, should we go into hydrogen? And the conclusion at that time was no, because we don't see a future for it. Here's why. You can simply reform the methane to produce hydrogen and carbon dioxide. You can produce a liquefied, the cryogenic liquid hydrogen, and distribute that. You put it in the vehicle, and on board, you use the hydrogen to drive a fuel cell. Now, that end use has to be by fuel cell, or the whole thing doesn't make sense. The reason why hydrogen might be viable at all is that you can get much higher conversions of chemical to mechanical or electrical energy using a fuel cell than you can by burning it. I won't go into the thermodynamics, but the Carnot limit, that thermodynamic limit on the efficiency of a heat engine, does not apply to a fuel cell. So the reason why hydrogen could ever be attractive is dependent on using fuel cells rather than combustion engines. Okay, so if you produce hydrogen from methane, liquefy it, store it as a liquid in the car or the bus or whatever, use that to drive the fuel cell, then you get about a 30% reduction in carbon dioxide emissions. Not a lot. Not a lot. If, on the other hand, you produce the methane, you convert methane into hydrogen, distribute it as a liquid, and capture the carbon dioxide from the steam reforming plant, capture the carbon dioxide and sequester it by putting it into geological strata, then you get a much larger saving, about twice. Okay? That's quite important. And there's one of the ways in which hydrogen could, in principle, be used. But it means that the steam reforming has to be done in large chemical plants where you can capture the carbon dioxide economically and transport it to, typically, geological strata under the sea. So hydrogen on its own actually doesn't work. You have to combine it with these other technologies, steam reforming in a large plant, capture the carbon dioxide, and sequester that to keep it out of the atmosphere. So there you can see why you get much more saving if you do that sequestration. In that case, the carbon in the methane ends up in the atmosphere as carbon dioxide, but in that case, it doesn't. It gets taken out of the atmosphere and put into geological strata. You can do a similar comparison, and here I'm looking at storing and transporting the hydrogen, not as a cryogenic liquid, but as a compressed gas. And as you can see, the figures turn out to be more attractive. The reason is that the energy which you need to cool the hydrogen and convert it into a cryogenic liquid is actually fairly substantial. And the losses are also significant if you have a vehicle standing around unused with hydrogen in it. Because obviously the heat gets into the cryogenic liquid and evaporates it, and you then got to either vent it or re-cool and compress it. So the energy, the parasitic energy losses there are fairly substantial. So if hydrogen has a future at all, it's going to be by that route. Now, there are people who still hang on to the idea that we can have a hydrogen-fueled transport sector, but it's got to be done that way. This also shows you, by the way, why distributing methane, converting it to hydrogen in the home, using that to run the fuel cell, that really doesn't work because you can't do sequestration on that small scale. In order for hydrogen to be viable, you need to capture and sequester the carbon that's in the methane. So that might be a way forward, but when you look at the economics of it, it's not actually terribly attractive. You're probably really better off using the methane directly as a fuel for heating purposes, and using your electricity for other purposes, and not trying to use hydrogen as the intermediate energy carrier. Well, I got interested in this a few years ago, and it seemed to me that if hydrogen was going to be viable anywhere, it was going to be on Iceland. Because Iceland has surplus electrical supplies. It also has no refining capacity. So things like gasoline and diesel fuel are imported into Iceland as finished products, and with a fairly hefty tax on them. So Iceland is also the place in the world which has the cheapest electricity and the most expensive gasoline. So if you're going to be able to switch from gasoline to hydrogen, Iceland is the obvious place to do it. Okay, so I went and had a look at it. And I could show you lots of interesting pictures, but there's one of them. That is a hydrogen filling station on the outskirts of Reykjavik, which is the capital of Iceland. And the great Icelandic hydrogen experiment actually amounted, when I got there, to 3 buses running around downtown Reykjavik. Okay, so you know, if you want to see the future of the hydrogen future, go to Reykjavik and take a ride on one of those buses, which shows you. Now, another issue with hydrogen is that people actually are frightened of it. And there are various approaches you can take to that. One of the reasons why hydrogen in the public imagination is dangerous is the explosion of the Hindenburg airship. This was a German airship which crossed the Atlantic to New York and caught fire when it arrived. And if you Google Hindenburg, you'll be able to see the old cine recordings of this airship catching fire and falling to the ground. When you look at it, actually, although hydrogen was blamed as the reason for that fire and explosion, actually it was the diesel fuel that caught fire. And you can see, if you look at the video, that what's burning is the shell of the airship, not the hydrogen. Nevertheless, this has got into public imagination as hydrogen is therefore dangerous. So when there was a trial done in London of hydrogen-powered buses, they didn't advertise it. They filled the buses somewhere out of sight, behind a warehouse somewhere. And if you just read the small print on the back of the bus, that was the only way of finding out that these things were actually powered by hydrogen. In Iceland, they took the opposite approach. They said, we're Vikings, we're going to go for this. And so the hydrogen filling station is actually on one of the main roads into Reykjavik. And the hope was that if the trial was successful, people would want to switch to hydrogen-powered cars and they could fill them up there. Now, there are no particular precautions. Here am I, and that is the hydrogen filling nozzle, which is used to charge the hydrogen into the buses. I'll show you the bus in a minute. So, that already shows you why, something I'll come back to later, why it's not enough to just look at a system as a set of material and energy flows. You also have to look at people's behaviour. Okay? And hydrogen comes with bad marks already. Now, this is just habit. I mean, if you were to start now and say, I've got a great idea for personal mobility, I'm going to have small vehicles and I'm going to power them with volatile hydrocarbons, and I'm going to keep the volatile hydrocarbon in a tank under the passenger seat, but it's okay because I'll tell people not to smoke when they're filling the vehicle. You wouldn't get away with it. It's just that we're used to it. So what the Icelanders said was, people will get used to this, let's just advertise it. And by the way, the hydrogen is considerably less likely to explode than gasoline. Okay. So there you are, that's how open it is. There's me at the hydrogen filling station. When you get on the bus, and there's the back of the bus, that's actually me there. It looks like any other old bus. These were actually German Daimler-Benz buses. I was lucky because when I went there, they were just being installed, so I got to talk to the engineer who was doing the checking before they went on the road. And I have to say that they were pretty primitive. I would have thought that if you were going to run a vehicle from a fuel cell, fueled by hydrogen or whatever, then you use direct current. These buses don't. They convert the direct current output from the fuel cell through a phase inverter to a three-phase supply, and then run a conventional three-phase motor with a gearbox to power the bus. Now, I thought this was bizarre, because starting from a blank sheet of paper, it wouldn't have been the way I would have done it. So I asked why, and the reason was quite simply, the Japanese have got all the patents on the DC applications. We've only got our own patents, which use three-phase. So we've got to do it using our technology. So there you are, there's another hint. If hydrogen vehicles get going, they will be Japanese, not German. But there are other problems. In order to use a direct current power system, you need permanent magnets, and the scarce metals that you need for permanent magnets are very expensive, and that's another barrier. So put the whole lot together, I got to the point of concluding that whereas before I went to Iceland, I thought hydrogen looked like a good idea, when I actually got there, I started to change my views. How do they make the hydrogen? Well, of course, being Iceland, it's done by electrolysis, and the electrolysis cells are at the filling station. So this is as efficient as it could be. The hydrogen is produced on demand by electrolysis and stored as a compressed gas at the back of that filling pump. So I can't imagine anywhere in the world where hydrogen is more likely to be viable. How viable is it in Iceland? Well, I managed to get a meeting with the Minister of Technological Development. This was in 2004, 10 years ago. I said, okay, this is great. I've seen your buses in downtown Reykjavik. What are you going to do with hydrogen next? And the answers were quite interesting. Well, we're not sure if it's viable. Economically, it's pretty expensive to produce hydrogen even this way and to use it to drive buses. Well, remember that if it's going to be viable anywhere, it's going to be Iceland, which has got the most expensive gasoline and the least expensive electricity in the world. So that was kind of a surprise to me. And what I was told by the government officials was that even with the tax on gasoline and diesel in Iceland, hydrogen was about as expensive as using gasoline or diesel because of the, mainly because of the cost of the electrolytic devices. Okay, so I said, well, yeah, but you know, these buses look pretty good. Are you going to replace all the buses in Iceland with hydrogen powered? And they said, no, we're going to stick with diesel. And there were various reasons given for that, none of which I quite believed, actually. The argument was roughly, well, if we change all the buses in Iceland to hydrogen, everyone else on Iceland is going to want hydrogen buses, and we can't do that much. Okay, so soft systems. Right, and the cost was unknown. So would you introduce hydrogen-powered cars? When you set up this filling station, very conspicuous, on a road into Reykjavik, are you thinking that people would use it? Maybe. Didn't get a definite answer on that one. So, okay, so then the sort of killer question, okay, fine. You've got 3 buses in downtown Reykjavik running on hydrogen. What else could you use hydrogen for? Well, bear in mind that fishing is a large part of the Icelandic economy. I've got a very nice picture somewhere, I didn't show it, include it here. I've got a picture of cod's heads drying on a rack. It's one of the places where Bacalhau is from, actually. So, well, what about hydrogen-powered fishing boats? Well, don't know. The seas are pretty rough around Iceland. The winters are pretty rough. I don't think we'd persuade fishermen to go out in boats with completely new power systems. It's what's called technological lock-in. People tend to go for what they know. So the best suggestion was, what are we going to use hydrogen for in addition to buses? Well, we're going to use it to power boats, which take tourists to see whales in Reykjavik Bay. And the reason we think that would be a good idea is that they're going to be quieter than conventional boats, so that you can get closer to the whales and the tourists will like it. Okay, well, so you can see, this is the point at which I came to the conclusion that hydrogen is not actually going to be the source of transportation in particular, but it's been trumped in the past. Things are still going on. I got an email this morning, just this morning, about future developments in hydrogen-powered cars. Unsurprisingly, the Japanese are continuing to push it because they've got the relevant patents. But there you are. System thinking tells me that hydrogen is actually not the basis of the energy economy of the future. Okay, so there's an example of system thinking applied to an energy carrier. Now let me move on then to buildings. And I'll start with zero energy buildings or near zero energy buildings. There's of course a European directive which is very loosely drafted, it's extraordinarily vague, but it promotes the idea of building and using buildings, infrastructure, which use no net energy over their lifetime. The idea is that you reduce energy use and provide it from renewable, non-carbon sources over the life of the building. But that statement already shows you why this is a flawed concept. Okay? There are things seriously wrong with the concept of a zero energy building. Here's a bit about why. You've got to see a building as a system. And in the last lecture, I pointed out the distinction between scope 1 and scope 2 activities, and I'll come on to scope 3 in a minute. Scope 1 refers to the greenhouse gas emissions from the activities which go on inside the building. I showed you an example of a car assembly line. Scope 2 says you've got to look broader than that, take more of a systems view, you've got to look at where the energy comes from and the emissions associated with that. The zero energy building concept tries to go as far as scope 2 because it looks at the energy supplied to the activities going on in the building. However, what it fails to allow for is the fact that buildings get built. And when they get to the end of their life, they get knocked down. So there are construction and decommissioning activities which are associated with greenhouse gas emissions. So if you're building a building, the cement and concrete in particular have significant greenhouse gas emissions associated with them. So do the metals that you use for reinforcement or fittings and so on. So the total greenhouse gas emissions associated with building something are usually substantial. And they're usually substantial compared to the emissions over the lifetime of the building. And then when it gets to the end of life, well, what you do with decommissioning depends on how you do it and whether you can reuse the materials or the components. So what I've done there is simply to say, if you're looking at the energy use, carbon emissions associated with something like a building, you need to look over the whole life cycle of the building. There's no point in simply concentrating on the operating stage, which is what the European directive does. Okay, so there's a conventional building. Just schematically, let's compare it with a zero energy building. Okay, so the zero energy building complies with the European or American directive. There's no net greenhouse gas emissions over the life of the building. But in order to achieve that, the construction needs to be different, usually more expensive, because it involves things like multiple glazing and insulation, and that's going to be associated with increased carbon emissions in the construction phase. And furthermore, when you get to the end of the life, with those additional material and components, the decommissioning impacts are likely to be larger as well. So I've drawn this diagram to be as kind as I can to the zero energy building concept. Okay, I've said, well, let's suppose that the additional emissions associated with the higher specifications here offset the energy used during the life of the building. Is that red line an improvement over the black one? Well, actually, no. Although you end up with total emissions being the same, it's actually worse, because you get more emissions in the short term, and by the time you've done discounting or applied the Lashoff method that I talked about last time, you come to the conclusion that what matters most is the short-term emission of greenhouse gases. So on that sort of time scale, a zero-energy building is actually likely to be even worse than a conventional building. Now, quite a few studies reported which have actually shown that zero-energy buildings are not anything like zero energy, and in fact they can be worse than conventional buildings. But now let's look on at the next bit, which is scope 3. Buildings in the context of urban metabolism. The zero energy building idea looks at the building in isolation. It doesn't look at how it interacts with other pieces of infrastructure, and in particular, it doesn't tell you anything about the way people behave when they use the building. There's quite a lot of work now being reported which looks at buildings as designed, buildings as actually constructed, and buildings as inhabited and used. And the three are completely different. In the UK, and my guess would be that this also applies in Portugal, a building as designed and the building as actually constructed differ very substantially. And the reason has to do with the skills in the workforce that build them. Now, in the UK, building workers are mainly Lithuanian, Latvian or Polish. And I don't know whether that applies in Portugal. And I'm not using that as a negative, because the Lithuanians, Latvians and Poles tend to be rather better at it than the British or the Irish or the traditional construction workers. But even so, an average construction worker is not trained to a level where he, usually he, can appreciate the reasons for all the things he's asked to do. Here's an example. Most buildings have double shells, okay, with an air gap in the middle. And that's important in order to maintain the insulating properties. If you ever look at a building being constructed, you'll see that the construction workers tend to throw their rubbish into the gap, including the drinks cans. Now, if you fill the gap between the walls with rubbish, including metal, there's a conduction path. Okay? So the insulation is never as good as the designer thought it would be. There are all sorts of examples like that. So there's the region between buildings as designed and buildings as constructed. Once it actually gets to the point where you've got people in the building, you've then got to ask, do they behave in the way that the building designer expected they would? Well, of course not. There's quite a body of work which shows that the energy efficiency of a building depends much more on the way it's used than on the way it's built or constructed. And it's the habits of the people in the building that matter. Okay, so let's explore that one a bit. What I'm talking about here is scope 3. Okay, remember scope 1 is what goes on in the building. Scope 2 is including the energy supplied to the building. And scope 3 includes everything else surrounding it. In particular, it includes things like transport. Okay? Because, so here's a building, maybe a work building, it may be mixed accommodation, it may be residential. But as well as the things that go on in the building, there are the activities which support what goes on in the building. And of these, the most important is probably transport. Okay? So there's transport of people to and from the building, transport of goods to and from the building, water used in the building, and waste, both water waste and solid waste. Those are all significant activities, scope 3 roughly, associated with the fact that the building is being used. And when you do the sums, it turns out that particularly transport is a large user of energy and a large source of greenhouse gas emissions. So you can make the building as efficient as you like, and maybe you can crack the problem of the greenhouse gas emissions associated with building it, but even so, people don't spend their entire lives in that building. They move to and from it, and goods move to and from it. And if the building efficiency is high, then transport takes over as one of the major sources of energy use and greenhouse gas emissions. And there's been some work done here in the Centre for Industrial Ecology which kind of illustrates that. But I'll give you the most stark example I know. There's a rather famous building development in Sweden on the outskirts of Gothenburg, at a place called Lindås. And these are buildings which were built to a very high specification so that they are supposed to be energy autonomous, which in the Swedish climate is quite difficult. The idea is that the insulation is so good and the ventilation system is so well designed that the buildings maintain an enjoyable indoor temperature just from the heat of the people who live there. Now, this is possible. A friend of mine in England had a specially built house which came in a flat pack from Canada, actually, and was assembled. And she found that it was so efficient that she actually had to go to high efficiency light bulbs because it overheated. It's possible, but remember the problem with transport. Lindås, this famous high efficiency energy development on the outskirts of Gothenburg, what they forgot when they built it was that it's nowhere near a bus route. So to get there and leave, you have to travel by car. There's no other way of doing it. And when you look at the energy use and the greenhouse gas emissions arising from those traffic movements, they more than swamp the savings in the energy efficiency of the building. Okay? So what I'm pointing out is that if you're looking at buildings as part of a system, you have to ask serious questions like, design the transport system as an integral part of the building, because if you don't do that, you're wasting your time. That idea is starting to get incorporated into some of the building codes on this side of the Atlantic, and particularly in the US. So they are starting to ask questions like, how do people get there? How does this relate to the transport system? And that tends to mean that new building is likely to be in the inner parts of cities rather than on the peripheries, which is probably a good thing. If you want to see a good example of that, go to Vancouver, where they've actually done quite a good job of developing what were previously poorly used land in the city and integrating it with the transport system. It's not perfect, but it's better than a lot of places. Okay, so there's a couple couple of examples of where the system thinking comes in. And now let me move on finally to another way in which behaviour comes in. Okay? I've already hinted that if you're looking at the efficiency of a building, you need to look at the behaviour of the people who occupy it, and that needs to be part of the design process. And this gets me to something which I think some of you will have come across, which is some work that was done by an economist in the 19th century by the name of Jevons. Jevons observed that improving the efficiency of, he was particularly concerned with industrial processes, Jevons observed that improving the efficiency of an industrial process sometimes led to savings in the short term, but very often led to increases in resource use in the longer term. And there are a lot of examples of that. Probably the best known these days is energy use in buildings. And it leads to the idea of rebound. The idea behind rebound is this. You can introduce a technological innovation which ought to make whatever, building, process, whatever, which ought to make the building more efficient so that it uses less energy and causes less emissions. That would be fine if people were robots. But what happens is that people tend to adapt their behaviour so that in a mild case, you simply don't get the savings you were hoping for. But in an extreme case, you can actually get more resource use and pollution. And I'll try to explain how that comes about. So rebound is people behaving in a way which reduces or maybe even counters the advantages that you hoped you were going to have. First order effects, sometimes called direct rebound, are actually fairly easy to understand and quite easy to see, actually. And as a rule of thumb, if you improve the energy efficiency of a building, for example by improving the insulation, you can work out how much energy that would save, and you'll probably get about 50 or 60% of it. And the reason is, pretty well universally, people react in a way which is called taking the savings in comfort. So particularly in Northern Europe, for example, if you insulate the building, you'd think that it will use less energy, but what happens is that the people who live there turn up the thermostat. Okay? They prefer a warmer indoor temperature if they can afford it. This can get quite extreme, and I've noticed this in particular in Sweden. It's probably clear I spend a lot of my time in Sweden. I have my own apartment in Sweden. And in the winters, in my apartment, I have to turn off the heating and sometimes open the windows. And the reason is this. The energy efficiency of Swedish buildings, measured in terms of insulation, is very high. It has some of the best building stock in the world. And the Swedes react to that by setting the indoor temperature to 24 or 25 degrees. Because if they're indoors, they like to go around in their underpants. Now, I find that very uncomfortable. I've got an apartment in a small, actually quite old building. The external insulation is very good, but the thermal insulation between apartments is lousy. So my apartment gets so much heat from the neighbouring apartments that if I want to keep it down to 18 degrees, which is what I like in the winter, I have to turn off the radiators and sometimes open the windows. So there's an extreme example of this form of direct rebound. If you compare energy use in UK and Sweden, it's a good comparison because Sweden has some of the best building stock in the world. The UK has some of the worst in Europe. And the energy use per square metre of indoor space is roughly the same in Britain and Sweden, which means that the Swedes actually use more energy to heat their buildings because they have more space than on average than we do in the UK. So there's an example of Jevons paradox. There are various other ways of approaching this. If you're an economist, you may have come across this as the Casaubon-Brooks hypothesis. But it's one of the best illustrations I can think of the phenomenon of rebound, which is people behaving in a way to offset what you thought were going to be big technological advantages. But it can get worse than that. The first order direct rebound is pretty obvious. But there's also a set of second order or indirect effects. And it goes roughly like this. Suppose I've insulated someone's house or apartment to make it much more energy efficient. They're going to take about 40 or 50% of those savings by improving the indoor climate. But that still means they're going to save 50 or 60% of the money. What do they spend that money on? You then have to look at what's called the environmental intensity of expenditure. So if I've got €1 or 10 euros or 100 euros, I can go out and spend it on something. And the energy use, the greenhouse gas emissions, any other measure of environmental pollution associated with that expenditure differs between different forms of expenditure. Actually, in Europe, it's pretty well constant over a broad range of activities, but there are some extreme outliers. There are things you can do with your money which have low environmental impact. For example, if you buy a good single malt scotch, which I seriously recommend, to me whiskey is one of the staples of life. If you spend your money on a really good whiskey, then you're spending it in a way which doesn't cause a lot of environmental damage. That's one end of the scale. High quality clothing is another one. Going to a theatre is a good thing to do. The energy intensity per unit of expenditure is usually pretty low. Not so for rock concerts because of the energy use, but that's by the by. So those are good things to spend your money on. So if you save your money on heating bills and use it to buy good whiskey, that's good. The other end of the range, anything that involves air travel tends to be very bad news. So what I sometimes tell my students back in England is, if you've got a few pounds and you want to cause maximum damage to the planet, buy strawberries that came by air freight from California. Because air freighted food has about the highest carbon intensity of anything. And it's even worse than one of the next bad things, which is air travel yourself. So there you can see there's another form of rebound. If someone saves money on their heating bills and uses that money for something which has a much higher carbon intensity, then not only do you end up not as far ahead as you thought you would, but you actually end up worse. Someone I know in the UK whose business is insulating houses says it really makes him cry when he puts in the insulation and then sees people taking weekend trips to Prague or moving in big plasma screen televisions, because they're actually offsetting all the savings which have resulted, the environmental savings, which have resulted for improving the insulation on the house. Okay, so those are examples of second order rebound. And they arise when people have a scarce commodity and something happens which removes the scarcity and enables them to devote it to something else. The most obvious one is money. Okay? Save money on your heating bills, use it to fly to Prague for the weekend, and you've actually damaged the planet much worse. Another scarce resource is time. And here's quite an interesting one. This is a form of rebound which has not really been analysed very much. To the extent that it's been done, it's one of my colleagues at the University of Surrey, Dr. Angela Druckmann, has looked into this. Next to money, the scarcest thing that most people perceive is their own time. So if you make some labour-saving improvement, which means they've got more spare time, you've then got to ask, what do they actually do with it? That one is really quite subtle. For example, it's often said that work patterns are going to change and people will spend more time working at home rather than in their office at the university or wherever. And this will save their travelling time. Well, it depends what they do with that extra time. And a few studies have been done, not very many, which suggest that if you give people more spare time by not requiring them to travel to and from work, what do they do instead is they go shopping more, which means that they drive to the forum or wherever and buy things. In effect, they're spending their time rather than their money in a way which causes more environmental damage. So I've given you those examples because I personally think they're quite interesting, but they also illustrate why it is that if you're working in an area which is called Energy for Sustainability, you really can't ignore the fact that people are not machines. And they will always find a way of offsetting any improvement that you think might come in. Jevons was probably the first person to comment on that, but it's a very real concern. So, for example, if you're improving the efficiency of a building, there's no point unless you also take positive steps to prevent rebound. If you simply improve the insulation on someone's house, they're going to set the thermostat differently. You've got to make sure that that doesn't happen. This is part of the policy, or environmental policy of a lot of European countries. It's anathema in the US at the moment. But the idea in Europe is sometimes called nudging. Okay, you've got to work out how you influence people's behaviour, because that is every bit as important as technological improvements. And I guess we're going to hear more about that around the time of the Paris conference. So here's my conclusion. People matter. And if you forget that what you're doing interacts with people, you're likely to be disappointed. And to me, that is an argument for saying that we need more work which involves engineers and social scientists working together. And it's tempting, as an engineer, to think that social science is easy because it's usually qualitative. No, it isn't. And having spent 25 years now, myself, working with particularly sociologists, it's a very different way of thinking, but it's also very constructive. There's no point in seeing a device as a machine manned by robots, when actually it's a building inhabited by people who have their own quirks and behaviours, and you really need to understand that if you're going to make any progress in the sort of area that we're all concerned with. Okay, I think I'll leave it there and ask if anyone wants any questions or discuss anything.
Okay, thank you very much, Roland. It was a great talk. We learned that we should drink whiskey. That's good for the environment.
Yeah.
Whiskey and not strawberries from College Park.
And for reasons I didn't have time to go into, the whiskey needs to come in a brown bottle.
In a round bottle?
Brown, coloured brown bottle. Whiskey in clear glass bottles is not so good as whiskey in a brown bottle. The reason is there's a surplus of brown glass, and Okay.
It's recycled.
Yeah, so you can recycle glass into brown bottles, but not into clear bottles. So there you are, there's your take-home message. Drink whiskey from a brown bottle.
Okay, so time for some questions. You can ask them in Portuguese if you feel more comfortable, and we'll try to translate. In fact, Professor Roland in a sense a bit of Portuguese, but we can help. Awesome.
Thank you very much for your time. It was a very nice presentation. I have just a question concerning the cumulative GHG emissions of the buildings.
Yes, do you want me to go back?
No, it's okay.
Okay.
The near zero energy building compared with the conventional building.
Okay, I will, I guess, and people know what we're talking about.
That is,
yeah.
So, to compare those two kind of buildings, so in the sense that the zero energy building will be worse at the end, taking into account the whole life cycle, I wonder if the construction and the commissioning of the buildings have a share so high as you can see in that graph. Compared with the energy used for, I don't know, 50 or 70 years
Yes.
of the lifetime.
If you go to a high efficiency building, the answer is yes. Okay? If you go to an existing conventional building, what you're saying is right, that the use dominates over the construction. But what I'm trying to do here is put it into the context of something like the European Zero Energy Building Directive, where you're looking at buildings which have a high use efficiency, but the directive forgets this aspect. Okay?
Okay. More questions?
Okay. This one needs a lot more exploration. You know, looking at the distribution between construction use and decommissioning. There's some very good work on odd spots of work. There's been quite good work on just what I know about. There's some quite good work done in Sweden by universities and the government agency for buildings, it's called Boverket. There's also been some very good work done in Canada, particularly by John Robinson, who used to be at the University of British Columbia, he's now moved to Toronto. No.
Okay, if there is no more questions, I will call again.
Thank you.
And if you want to discuss anything in particular with Professor Roland, Clift, you'll be here until the 25th of this month.
Yes, another week.